Greetings from Istanbul Technical University. I'm Salih, the team lead of the IT Rover team. Today we proudly introduce our latest rover, ITU AXA Rover. Founded in 2016, over the past decade, we have gathered students from a wide range of disciplines to explore the world of space robotics. Today we are a diverse force featuring talents from all faculties across our university. The development of a complex system like a rover requires precise coordination. The operational structure of our team is defined by specialized divisions. Operating under the management of the team leader, our organization is composed of 6 sub-teams: mechanics, electronics, software, science, organization, and design. Furthermore, to ensure seamless engineering integration, all technical sub-teams conduct their operations under the supervision of a technical team's leader. The mechanical sub-team focuses on the physical architecture and the actual manufacturing of the rover. The electronics sub-team builds our embedded systems from the ground up, directs power distributions, and produces our custom-printed circuit boards. The software sub-team codes the advanced algorithms and integrates them to make the rover function perfectly. The science sub-team simulates Martian geology and biology, carrying out vital experiments to analyze surface conditions. The organization sub-team secures sponsorships and keeps our financial planning on track. The design sub-team shapes our brand identity and produces the content for our social media accounts. We compete in the European Rover Challenge to measure ourselves against the highest global standards and to see how far we can push our limits. We are here to drive innovation in space exploration, motivate tomorrow's engineers, and proudly represent our country internationally. We are ready for the European Rover Challenge 2026.
Our rover features modular solid aluminum framework that has high-strength carbon fiber central tube as the primary load-bearing spine. This robust chassis is integrated with refined curve suspension system and upgraded differential bar, ensuring stability and smooth weight distribution to navigate unpredictable topography by forward and backward moves as well as right and left turns for smooth traversal. Mobility is driven by 4 brushed DC motors which are fully encased within aluminum hubs for environmental protection. The drive system is powered by custom-engineered wheels featuring shock absorption ABS rims and 3D printed TPU tires with stable footprint, optimized for vibration damping and maximum traction. This configuration maintains a 30 cm ground clearance and while adhering to competitions fits strictly within the required 1.1 m3 dimensions. The electronic box serves as center control, power management, and communication are powered by 42-volt lithium-ion battery. A custom power distribution board utilizes high-efficiency regulator circuits to convert this power into stable 24, 90.5, 12, and 5 volts rails for drivers, controllers, MPUs, and sensors. For safety, the architecture incorporates 2 independent emergency stop mechanisms. One that cuts power strictly to drivetrain and robotic arm actuators to help motion, and the second that completely shuts down the entire power network. Precise motion is achieved via PID control algorithm processing feedback data using integrated Hall effect sensors for drivetrain speed control and encoders for robotic arm joint position control. All actuator commands are RSP messages used in competition and sensor data route through various protocols including CAN bus, UART, iSecurity, SPI, and internet-based communication over LAN to the rover control unit, a custom ARM-based microcontroller board servicing as primary controller. The RC manages drivetrain and ARM motor drivers via CAN bus interface, communicates with the base station over a local network infrastructure, and handles distributed sensors and actuators such as magnetometers and modules. Finally, wireless connectivity to the base station is established via dual-band 2.4 GHz and 5 GHz Wi-Fi antennas complemented by an adjacent RGB status LED to indicate different operational states of the rover. The IT Rover system operates on a ROS-based hierarchical manager interface architecture that seamlessly integrates strategic planning, hybrid localization, computer vision, and precise manipulation. In autonomous navigation, mission goals like local waypoints are defined by the goal controller and translated into dynamic strategic decisions by behavior tree structure as pie trees within the mission manager. These decisions are then processed by locomove-based navigation stack using NavFN and EVB algorithms to drive the vehicle. In absence of global positioning, the system relies strictly on wheel odometry and a LiDAR image sensor suite. The LoRa/SLAM algorithm processes LiDAR point cross-cloud tightly coupled with IMU data to provide high-precision mapping and robust localization. Concurrently, wheel odometry is processed through the extended Kalman filter block to generate stable baseline odometry for navigation stack. A proprietary camera UI system optimizes and dynamically routes video feeds to computer vision nodes and the operator interface supporting both real-time AR marker detection for navigation and vision integrated manipulation for 6 degrees of freedom robotic arm. Managed by ARM Manager, the manipulator's precise movements leverage analytical and numerical solvers within the MOVEIT framework related with PID loops and ROS control and validated in gazebo simulations. Environmental sample evolution is handled by Science Manager and its interface, converting drilling and collection telemetry into interface GUI graphs. Finally, base station operations are maintained over a low latency RF bridge transmitting joystick and web GUI commands, while the centralized CAN interface completes a closed-loop control by translating high-level manager commands into industrial CAN open row CAN protocols for motor drivers and physical sensors.
Our drone includes several major updates compared to last year. We have deployed a new frame design with brushless DC motors as our propulsion unit and continued using the Pixac 248 flight controller with Pilot firmware. For autonomous flight and probe detection, we integrated a Raspberry Pi Model B companion computer running our custom MATLAB algorithms with onboard 360 degrees camera support. We also added an AirMax Bullet M2 antenna to improve communication range significantly. All algorithms are first tested in simulation environments such as Gazebo, Simulink, and Arvis before real-world flights, allowing safer deployment and operator training. Finally, we implemented fail-safe systems for RC signal loss and low battery conditions to ensure safe and reliable operation.
The robotic arm system consists of 6-degree 3D manipulator engineered to manage wide variety of payloads, exceeding 8 kilograms, ranging from delicate electronic components to heavy geological samples. This year, we have improved mechanical architecture driven by custom-engineered cycloidal reducers delivering high-torque transmission with near-zero backlash for fluid vibration-free motion. To achieve high precision, the control stacks employs a closed-loop PID architecture utilizing encoder feedback via CAN-FD bus. The software environment utilizes ROS and MOVET inverse kinematics to calculate exact joint trajectories for complex maneuvers, with every operation validated through gazebo simulations. Supported by integrated USB cameras for vision feedback, the arm's gripper mechanism ensures accurate interaction with complex devices, including opening drawers and placing boxes inside, as well as inserting the plug into the socket, setting off lower switches, turning rotary control and rotary power switches, and placing electromagnets safely. Beyond the ERC panel, the arm easily handles tools like mallets and screwdrivers, moreover collects rock samples and probes, and also keeps on board the rover throughout the mission. These advancements guarantee the rover's capacity to overcome complex operating difficulties with high reliability and robustness during field operations.
Sitting 7 to 8 kilometers below Dedham, Hellas Planitia is Mars's deepest impact basin. This high-pressure zone provides suitable thermodynamic conditions, permitting liquid water stability. To maintain safe landing and mobility, we must mitigate risks from slope instability, locate debris stop-runs, and honeycomb terrains. We utilize JMARS to select the ideal landing ellipse with slopes under 20 degrees, low boulder density, and safe thermal profiles, mapping a 30-kilometer traverse across 3 high-priority regions of interest. Our geological workflow decodes local stratigraphy and chronology by cross-referencing file mapping with high-resolution imaging. Our sensors measure regolith pH, temperature, pressure, and humidity to detect localized habitability and biosignatures. We are employing nanotechnology-based detection systems to monitor and identify key biosignatures. We analyze glucose through RGB-based analysis and quantify riboflavin, ATP, and nucleic acids with spectrometry. Additionally, we screen for free amino groups via the nitrogen assay and utilize the Bradford assay for biological validation. Real-time panoramic camera arrays ensure full situational awareness and detect unexpected dynamic hazards. For scientific validation, an integrated UV with spectrometer identifies biomolecules, while a compact Raman spectrometer detects our target minerals. This year, we integrated a dual magnetometer system correlating rover and base station inputs to deliver highly accurate data and generate high-resolution magnetic maps, precisely identifying geological structures like faults and fractures. Our drilling mechanism includes sampling and sample catching system, and its operational limits enable a drilling depth of 30 centimeters and acquisition for 100 grams of soil sample. Upon core extraction, the catching executes a linear soil compression via high-torque loaded assembly. Thus, isolation of our sample from environmental factors is maintained without any contamination, guaranteeing analytical viability.